Okay, I've got 101, everybody, so I think we'll get started. Good afternoon. My name is Jerry Hahn from Purdue University CERIAS, and I'd like to welcome you to the July 29 session of the CERIAS Summer Security Seminar Series. We're very pleased with the lineup we have in place and hope you'll benefit from hearing from the cybersecurity experts we've assembled for you at these weekly seminars. These sessions would not be possible without support of the members of the CERIAS Strategic Partnership Program. To learn more about CERIAS and the CERIAS Strategic Partnership Program and how your organization may benefit, please contact info@cerias.purdue.edu. During the presentation, please keep your line muted. If you have a question, please submit your question through the Q&A function. We'll also be monitoring the raise your hand function at the website, and we'll try to get all the questions responded to before the end of our time. It's my great pleasure to introduce our speaker for today. Carter Bullard is a longtime friend of CERIAS and has been recognized as an expert in cybersecurity and a leader in the development of network security technologies and practices for over 35 years. His professional experience includes research and development in cybersecurity at U.S. national laboratories, federally funded research and development centers, and the telecommunication industry. Managing security products and service development at leading network vendors such as 4Systems, Bay Networks, and Nortel. Leading network security standards for the ITU, ATM Forum, and IETF, and providing cybersecurity consulting to the NSA, DHS, U.S. Department of Defense, NSF, and the FBI. Carter is the inventor of NetFlow and is a recognized subject matter expert in network cybersecurity, active cyber defense, situational awareness, network measurement and monitoring analytics for cybersecurity, and security control assurance. He holds a BS and MS in pharmacology from the University of Georgia and has held faculty research scientist positions at Carnegie Mellon and at the Georgia Institute of Technology. So with that, I'll turn the floor over to Carter.
Thanks, Jerry, and thanks so much for the opportunity to talk about some of the work that I've recently been doing. So good afternoon, everybody. I hope everybody's safe and everybody's having a great day. For those on the West Coast and in that direction, good morning. And for those in the East Coast and going the other way, good afternoon and good evening. I'm going to present to you some work that I've done relative to predictive analytics and networks using network awareness data. Let me see if I can share my screen real quick and we can get started. I think I'll share the whole screen and then start on the presentation here. Let's see. There we go. The key here is that we want to do a lot of predictive analytics, new cybersecurity awareness capabilities, specifically for the endpoint, and that's what is going to be the focus of the conversation for today. So you're going to hear an awful lot more about system architecture, issues, problems, and around moving this kind of technology into the endpoint rather than the actual analytics themselves. But hopefully you'll get a good sense of what the work has been and where we're going to try to take it. So as Jerry was saying, I've done an awful lot of stuff in the world over the last few years, last 30-something years. And the most recent has been working on a project at one of the independent SOCs at DHS on trying to eliminate the unmonitored space in the internal parts of the enterprise network. And that's been a very successful project, limited, but it's been very successful. And I'd like to talk to you about that today. So this way. The problem that they have is like the problem we have in many enterprises where I have to move this that way. There we go. Is that there's unauthorized data access and data exfiltration being initiated from inside the enterprise. We do all this amazing cybersecurity protection, spend a lot of money to harden infrastructure to protect the external and boundary interfaces from access, but it still is happening that there's a lot of unauthorized data access and data exfiltration because the endpoints are very susceptible to malware exploitation through a number of means. And so it's difficult to completely protect a large enterprise, even through user training and a lot of technology. And when you extend this model to what's going on today with a lot of remote and mobile assets coming and going in and out of enterprises, there's real opportunity for undetected malware to get onto these mobile assets, and then to cause a lot of problems inside the enterprise when they return, regardless of the fact that they have CDM, HBSS, and EDR style protections. These are US DoD and US government acronyms. And then when you look at what CISA, which is US DoD, or DHS, Computer Information Security, my screen, this thing. Okay, let me go back. I've lost. Let me go back to this one to finish this one. So the CISA, Interim Telework Guidance message that came out recently is a really important thing that's going on in the government, where they've developed a lot of cloud-based services, and they are suggesting that people from home or remotely to go directly to the cloud provider to get to their assets and to create communications for work. And of course, that bypasses a lot of protection that these infrastructures have spent a lot of money to develop to protect these remote assets. So when that happens, you've got some serious potential problems that can occur for endpoint security. So I believe that this is a job for predictive analytics. Predictive analytics for the CISO that really has responsibility for the endpoint, maybe not for the end user so much. But you do need to get ahead of the game, so to speak, to provide a heads up that an asset has a significant opportunity to attack the infrastructure when it attaches to the enterprise. And what I mean by that is if I've been traveling and I've been going to a hotel, or if I'm at home, when I attach to my enterprise, there's a great deal of opportunity that I've been exploited, and that there's some kind of agent on my system that is going to try to do some things with the enterprise once I connect. Now, if we know that a remote or mobile node has interacted with a bad actor or exhibited bad actor behavior or victim behavior while they're outside the enterprise, we would be able to realize that at some level that it can have a significant impact on the organization. If we know that, we can adjust how that end system might interact with the enterprise going forward. Now, can we estimate the potential of a network asset based on its historical network behavior? I think yes. I think if you know what an asset has done in the network, every packet accounted for, have categorized and classified what it's been doing in its behavior, yes, I think you can do that. Let me go back. And but how do you realize this kind of approach with today's technology? And the answer is that you need a lot of data, and you need a lot more data, and you need even more data, and then you need some more data. But it's not just any data. So I think it's going to be a break from the traditional SIM type approach to cybersecurity, and we're going to have to introduce new data in order to approach doing predictive analytics in this kind of an architecture. And I think it's inevitable that this happens. So I'm really happy to talk about this and the work that we've been doing around this. So I've been talking about this DHS Elimination of Unmonitored Space program. This is the pilot that I've been involved in at the Office of Inspector General of DHS. It was a private little pilot. It's a small effort by the CISO there, the two CISOs that have been there over the last 2 or 3 years. And it's been pretty successful. Now, working with an organization like this, and you want to introduce a new kind of widget or a new kind of capability, it's better if you can fit it into a long history of effort within either a government approach to cybersecurity or at least some kind of NIST or some kind of framework. So we've decided that we were going to approach this problem of mobile assets and endpoint sensing by adopting well-established government cybersecurity programs. And in particular, we chose the NSA's Integrated Active Cyber Defensive Program and the US DoD Centaur and Acropolis programs. Now, these aren't, not a lot of people know about these, but they are advertised and talked about on the web. The IACD program is now in the OASIS project, and it's well developed and it's active. So we'd like to talk a little bit about that in the next couple of slides. We use Argus to generate network flow system data, and that's a technology that has been integrated into Centaur and Acropolis over the years. and is a part, has been discussed in the Integrated Active Cyber Defensive Programs. So when you go to DHS-OIG and talk about inserting new technology, framed it around the notion of an IACD project and a Centaur Acropolis approach using a sensor that they have already been using in the infrastructure. And so Argus is being used in the NGS, NGX, and JRSS program at DISA. And we use it to generate network sensing data, and we process it in order to do network sense making. And those two concepts are really important to the strategy and the architecture and the approach that makes it feasible to do. So we are going to introduce network awareness into the endpoint, and we're going to try to enable this awareness to support identification, protection, detection, response, and recovery for cyber incidences within this particular pilot enterprise. I think you need to do that because that's the whole life cycle. And if you introduce new technology, you really do need to hit some aspects of all aspects of a cyber incident response. Okay, here. The IACD program is really important for a number of reasons in our strategy for doing what we're doing here. They broke the concept of incident detection, analysis, and response into four basic components: sensing, sense-making, decision-making, and action. And it was a formal architecture. And our approach implements a formal network sensing and sense-making, just as they basically presented in the reference architecture of the IACD. And we actually took a literal interpretation of that and made these completely independent distributed functions, where you have sensing totally independent of sense-making. And by separating those two concepts, we can approach doing endpoint cybersecurity predictive analytics in a scalable and a way that the industry, I think, would actually accept it. Okay? The Centaur and Acropolis programs are really important because they talk about simply collecting, storing, and analyzing network traffic. They don't talk about analyzing it and developing mitigations and strategies and all sorts of life cycle systems. They're just talking about creating data, collecting it, and storing it. And that's a really different approach than you see in conventional cybersecurity products, where they want to actually integrate it all into mitigation. Why would you do something if you can't protect against it? It has been a theme throughout the whole kind of last couple of years of cybersecurity products. But we adopted this Acropolis approach because we're really interested in trying to enable something that doesn't necessarily lead to specific mitigation. And so we want to uncouple that. We want to use the IACD architecture to uncouple components so that we can actually deploy something in the real world that's going to actually work. And so, let's get to that. So the whole concept of this program is to expand network sensing, predictive analytics to the edge. So if you look at a traditional network architecture, you see in a massively complex diagram. And the most important part of this diagram are that there are two little sensors right here. If you look at how things like Einstein, JRSS, all the big systems, how they work is they're really limited sensing right at the enterprise border edge. And that's about as much visibility as they get. As long as traffic goes end to end, you're going to see it and you can do something about it. But if you have activity down here in an end system, these sensor deployments can't see that kind of traffic. So we're proposing the same within some very complex architectures to deploy sensors everywhere. And the key, and through that additional visibility of the network traffic in all these different places, you can finally eliminate the unmonitored space and see what's going on. Now this falls into the cybersecurity marketplace as an endpoint detection and response product or effort, so the EDR product. So the hardest part about getting new technology into EDR systems is that you don't have any cycles, or you don't have any battery life to put too many more additional functions on the endpoint. And nobody wants another agent. Nobody wants to add a lot of software. So it's going to be kind of hard to introduce new capabilities like predictive analytics for the endpoint if you put it all in the endpoint, because it just, as we all know, a lot of these capabilities, especially machine learning, neural networks, a lot of this processing can be cycle intensive for certain aspects of the function. So looking at the EDR approach, trying to understand what can we deploy and how do we architect it and what can we do in order to get some functions, our approach is to separate the advanced network flow data generation with endpoints from the data processing. So all we're going to do is generate network flow data on the endpoint with no analytics, no event generation, no alarms, no alerts. We're just going to create the data and then pull the data off the systems and do the hard work somewhere else. Okay, the primary benefits of doing this is that we get the network forensics data generation. Whether the data is collected or not, if we have a network log of what's going on every end system in the enterprise, then we have something that we had that improves what we had before completely. So at least we have a new audit log that allows us to do forensics analysis. Now, if we can take that data, we can get contextual visibility regardless of where the endpoint is. So when the endpoint leaves, goes home, goes to the hotel, goes to the airport, all the things that we want to do when the COVID stuff is over, we have the ability to see what network experience this endpoint had. Now, if we can get this thing to where we can generate this data with very limited CPU utilization and memory utilization and disk utilization, then we've got something that we actually can use in the real-time world. If we got that data, then we can do the analytics that we need, assuming, of course, that we have the right features and the right metrics and the right formats for the data that allows us to do the analytics that we need to do. Now, having this kind of visibility on the endpoint will allow us to see the really sophisticated cyber techniques that are being used today. All the shadow IT, the tunnel accesses, covert channel, and entry points into the enterprise. So putting this capability on the endpoint we think is very important. So we've spent a lot of time trying to get this piece of software into this endpoint so that it would work for these guys. We definitely want to have an opportunity to provide near real-time access to this data for operational purposes. And of course, it's going to be cost-effective to just turn on your laptop or your endpoint or your wireless access point so that it can be a sensor rather than having to buy a bunch of sensors. Okay, well, the resulting framework that we came up with is a data analytics framework that you can read a lot of papers about this kind of approach, not specifically to ours. It's a notion that we have remote data generation, collection, and processing in a centralized sort of framework is a very popular strategy. And if you look at it closely, you'll start to see that this looks like a cloud-enabled MSSP type of function where we're taking the customer's traffic, pulling it into a centralized sort of analytic, doing some stuff on it, and creating results that will allow us to do better security. And the reason I've gone through all of this stuff is if you want to introduce predictive analytics to an enterprise, you have to have the data to drive the model development, the model training, the model optimization, and then you have to have a data source in order for the model to actually operate in a live environment. So in order to talk about predictive analytics today in large enterprises and operationally, you have to talk about the data, and you have to talk about where's the data going to be generated, where's it coming from, who's collecting it, where's it going to be, how many cores have I got, how much memory have I got. And so I started this whole effort realizing that I had to work on the data. So, so now I brought you up to where we are to start this process. So, okay, so in the operational pilot that we have, it's been very successful, and we've demonstrated that we can take this network sensing and sense-making approach and enable new capabilities for the component. Now understand that at DHS, we had a mixture of sensors. We have appliances, we're pulling in existing flow data, we're supplementing that with endpoint flow data so we get a complete picture of what's going on in the enterprise, because remember we were trying to eliminate unmonitored space. And when you have an endpoint like a switch, control port, or a DNS server, or a big honking server, having sensors just on the endpoints doesn't cover it completely. So, but in the process of eliminating the unmonitored space for the whole organization, we created data sets and data audit archives that allowed us to do an awful lot of interesting and new analytics for the enterprise. We're very successful at doing what at DHS is called SOC notification investigation. They have tailored third-party intelligence information that they develop and send to their SOCs. And we can use our historical flow data that we have generated and collected into these centralized servers to investigate those in an automated fashion. So that's worked out really, really well. We've identified new malware this way by doing behavioral anomaly detection on, let's see if I can go back here, on the data. We've been able to look at critical infrastructure, architectural assurance, which is really important. Most places like universities are being broken into by the introduction of rogue servers, like rogue DNS servers, DHCP servers. And if your endpoints, and you have many sensors, especially in your endpoints, can give you flow information about who did this endpoint use as a DNS server, or who did this endpoint use as a DHCP server, you can identify rogue servers inside your infrastructure, and which is huge, by the way. It's really important. So we feel like we've had some really big successes taking this approach. And the last part of the approach was, once we had this framework for generating the data from the endpoints, collecting it and processing it in a centralized environment, we now can approach doing some really advanced stuff, such as predictive analytics. Now, predictive analytics are kind of interesting. You know, you're predicting the future, or you're predicting the present. I'd say you also need to predict the past. And when you realize that the timeline in terms of analytics and your event understanding of what's going on in an infrastructure because there's delay, or you're looking at historical data, the concept of what is predictive and what's the future isn't really well set. So you can basically slide the timeline around and create an environment in which certain types of analytics become predictive because you know what the outcome is going to be. So for instance, if you know that this end system has been infected with malware, you can predict that he is going to, or she, or it, is going to be able to impact the organization in a negative way. So just malware detection can be argued to be a predictive analytic in some environments. Now we take that concept a little bit and stretch it out, and so we're going to use discrete and continuous predictive analytics and machine learning to identify intrusions and anomalous network behavior for the endpoints while they're outside the enterprise. And that means that we're going to use traditional STIX taxi messages. We're going to use traditional IDS capabilities. We're going to use body of capabilities, the thousands of papers that have been written about machine learning and anomaly detection for intrusion detection. And we're going to use those techniques to do classic cybersecurity identification, and then use those as weights and for features for doing machine learning for all the behavior of all the remote assets that there are in the enterprise. I'm going to back this back up. I don't know why it's going forward. So by having the data that we generate on the endpoint and bring it to a central server, we create an operational large data approach that allows us to begin to approach machine learning model development and training. And that's, I think, one of the biggest problems with machine learning for enterprises is that they don't have any data, and they don't have any good labeled data. And they don't, and many sites have site-specific behaviors. So to take a machine learning algorithm that's really great on a data set that is simulated, for instance, and bring it into an enterprise and try to run it, it doesn't quite work out so well. So the answer to that problem is to create your own data and to use your own data to develop your own predictive analytics and to train them. So this system of creating the data, collecting it, analyzing it, massaging it, and managing this large data set is really prime for doing predictive analytic development, especially machine learning development. We're going to use training features like ports and protocols, communicating peers, the services they use, how much resources they use, geospatial and net-spatial dimensions, and things like that, to give us a sense of, is this guy normal? Is he normally behaving in this organization? Or has he got some anomalous behavior? And we're going to use that to score his potential for having been intruded or having been affected by some kind of cyber behavior. We're going to add to that, and that's pretty much the classic way that the literature does this kind of stuff. But we're going to add to that this third-party intelligence that we get from DHS or from the commercial intelligence providers. It's going to help us to realize that this guy talked to a bad guy. This guy talked to a known bad guy with a bad protocol, or this guy downloaded some email and did something bad. Now, that type of scoring is really huge for machine learning. It reduces false positives, and it really gives you some great sort of responses. So the merging of flow data captured from the endpoint, brought to a centralized server, supplemented with third-party intelligence data, sticks, taxi messages, and reputation data to give us an ability to score an endpoint while it's outside the enterprise to understand, is it a threat to the organization? Okay, so there's a lot of precedence for this type of work. Argus was used to develop UNSW NB15, which is a huge intrusion detection data set, and it's used in lots of AI cybersecurity research. Argus was used in this particular model because it has specific features that are really important to minimizing false positives and false negatives. We have inter-packet arrival times, jitter information, round-trip times that you don't see in other flow data sets. And really people have written a lot of papers about the benefits of having additional features in their sets for doing predictive analytics and intrusion detection. Now Oak Ridge has used our data to do their unsupervised anomaly detection system, which is really a great system, the C2 stuff they did at ORNO. And the last NSF Advanced Measurement Initiative used Argus data to do Markov chaining modeling for large-scale infrastructure. So these types of predictive analytics are things that the Argus project has supported in the past, and we have used these at DHS successfully to establish that an end system, for instance, has seen a bad reputation and that we can expect that he might move into a less secure sort of set of behaviors. So having had that experience with Argus data has really been very helpful. But we also want to focus the data analysis and the predictive analysis so that we can actually understand the real threat potential of mobile assets when they come back to the enterprise. So the best way to do that is to do multi-endpoint classification schemes that contribute to the cyber score. Now, so what I mean by all that stuff, and it might be confusing at this point, but the idea is if I have an end system, it's got a name, it's got an address system, and I can say that this guy is a browser and he uses these three flow features. He uses these internal services to get his basic background processing done. Then I can track that as he moves in and out of different environments and see if he has any changes. The biggest problems we have with mobile assets is that they come in and they suck up a lot of data because they're really exfiltration nodes, but they don't express any of the bad behavior until they leave the enterprise. And so we need to be able to identify that this asset is moving around and see a whole different set of behaviors in one context different from another. And by using machine learning and predictive analytics within a context, we can identify that this guy has a completely different personality here than he has over here. And that gives us the ability to say that he has a different security posture, which suggests that he may have a threat potential for the enterprise that we wouldn't have seen if we hadn't done this kind of analysis. And that's really the big deal for this approach, to be able to see this. Okay. So what do we want to see with these guys? Well, we want to see if there's any indication of successful intrusion. We want to see STIX taxi signature analysis, control plane manipulation, any association with other bad actors like reputation. We want to see if there's been any exfiltration behavior when they're outside the infrastructure. Have they used any covert channels? Do they try to do discovery or lateral movement behavior when they're outside the organization or inside the organization? And we also want to know, do they have context-sensitive victim behavior, which means that they provide permissive access when they're outside the organization that they don't express when they're inside the organization. Malware is smart enough to use these techniques, and a lot of people are starting to see context-sensitive malware. And so if we can do these simple little observations through predictive analytics, machine learning analytics based on the behavior that they express outside the organization, we'll have an indication that these guys have the potential to impact the enterprise in a negative way when they do return. So each one of these would probably represent a different predictive analytic, a different machine learning model, a different set of criteria and features needed to make a distinction. And so having a large-scale analytic architecture that allows for hundreds of different machine learning algorithms to work on a single data set at a time can enable this level of complex analytics that are needed to do a good job with this approach. And that's why talking about the data, where's the data come from, the kind of data that it is, and having an architecture for the data is so important, because when you finally get to it, you realize there's not one predictive analytic, there are hundreds of analytics you want to run on this stuff. And so you need an architecture that allows you to do that when you deploy this in an operational system. People always want to see graphs. So this is one of our exfiltration behavioral baselines that we do, where we're looking at one of our metrics, the producer-consumer ratio. The idea is that this guy, when he talks to this set of web servers, he pulls data down. He consumes the data. If on another day in a different context he talks to the same guy, but he produces data, he pushes it to that guy, that could be an indication of exfiltration. And an analysis of a really sophisticated exfiltration effort is pretty complicated, and you need to be able to do things like this on every flow, on every port, on every protocol, so that you can see striped strategies and very sophisticated strategies for moving data out of a particular endpoint. So we have lots of graphs and lots of analytic capabilities to see anomalies. And we can find covert channels. Here's a DNS covert channel example. All 5 of these are normal DNS servers. This is the ratio of how much data comes back in a DNS response. Oh, and by the way, these are millions of transactions, not hundreds or thousands. These are millions. So we have really good baseline data. And these are covert channels. The one on the right is really different from any of these guys, right? You can tell immediately that something's up. So we have these kinds of covert channel analysis that are very simple for machine learning to develop. People say that you need to have training data to show that this is an attack, this is normal, this is an attack, this is normal, this is an attack. But some of these are so easily detected that you don't necessarily have to tell the machine learning that this is, you don't have to give it purpose labeling. You can just say that it's different and it'll pick it up. So Okay. So the idea is that we've instrumented these endpoints. They've gone out and they're coming back. We've been watching them for quite some time. We have a sense, based because of the data that they have generated and held on their own disks. We've collected that data and done a bunch of analysis, and we have a baseline of what's normal. And then as they come and go, we can, and when we get the opportunity to collect the data, we can analyze them to see if there are huge anomalies associated with them. We can use machine learning and we can use predictive analytics based on those changes to understand if this guy has a greater impact to attack the infrastructure. And this has worked out pretty well so far in several organizations. It's still got a lot of work to do. It's still early in its concepts. Being able to do hundreds and hundreds of machine learning algorithms on a single architecture has proved to be the key to making this approach work. And so that's why I talk about data first and then the types of predictive analytics that you can do second. And the thing is, the literature supports thousands and thousands of approaches on this. So even one particular predictive analytic is difficult to talk about. But when you do this and you do get these scores, what do you do now? And the idea is that you can't just simply stick this data on a disk and keep going, because you have to do something with the information. So you take these predictive analytics scores, you need to make them available to the traditional cybersecurity management framework that the enterprise normally uses. Many enterprises don't have much beyond SIEMs, and I don't want to talk about specific products, but centralized analytics and visualization processes around traditional security alerts, I think is the best way to talk about it. Here, we can tell you that this endpoint has a higher potential because we think that he talked to a bad guy while he was gone and then he came back. That would add many, many, many more alarms and alerts to an already large heaping pile of alarms and alerts. So it's not just enough to create alarms and alerts. You actually have to create APIs to fetch these cyber scores so that you can understand which ones are there. You have to be able to query them and search them. And then when you see a score that seems unreasonable, you have to be able to peruse the data and evaluate for yourself whether the analytics and the machine learning actually giving you a reasonable score. So just to simply have an analytic and place it in an end system and have it go red, yellow, green isn't enough anymore. It has to fit into a much larger infrastructure. And so, so it's focusing on the EDR sort of side of things and recognizing that put something in a sensor in an endpoint, well, there are massive technological hurdles you have to overcome in order to get that to work. We think the DHS project did a good job at that. So I think we can actually instrument the endpoints to create the data now. And to move that data effectively into an analytic is definitely a doable sort of thing. Creating the scores actually seems to be an approachable thing, but the choices of predictive analytics is very, it's an art. Now there's no scientific basis on why am I looking for this kind of intrusion or why am I looking for this kind of exploit. That really grows from an experienced SOC in a large organization. So one or two of them is great. When you get to 50 and 60 of them, you have to really now start to manage what it is that these things are telling you. And so, and it has to integrate into a system where you can manage the awareness as you manage other cybersecurity events. So integrating it into a system that has human-in-the-loop capabilities so the human can modify the scores and peruse them is really, really important. But I think the key here is that you have to be able to make this data available to SOAR technology. So when an endpoint comes back and you realize it was trashed while it was gone, you really want a piece of automation to keep him from connecting to the infrastructure in a complete way, because you know he's going to have the potential of causing some damage. So having a process where SOAR can isolate devices based on the data that it provides to say, this is what I did while I was gone, have it evaluated, and do a score on it, and then to make a decision as to whether he should or shouldn't get in, is I think an important part about how this might fit into an enterprise and how this might go. So I think my conclusions out of this work are that the technology is feasible. We can instrument the endpoint if we divide and conquer the capabilities so that we're just creating the data on the endpoint. We're not analyzing it, generating alarms and alerts, and we're not trying to put the GUIs and everything on the endpoint. We can split the functions so that we have minimum impact on the endpoint in terms of resources, CPU, disk, and memory. And then when we pull that data in, it could be immediately, it could be real time, or it could be a month later. And the notion is that if it's a month later, can we do something effective with the data to give the enterprise, the CISO, a good look as to what's going on and to understand what has it been doing to my enterprise over this time. I think this is definitely an approach that can work. And I think that the data that it generates can be useful, but it does come with its caveats. The notion is that you don't want to be overwhelmed with a whole nother set of data. But if you can integrate it into an effective system that can use predictive analytics in a useful way, then I think it's going to bring a lot of benefit to the enterprise. And if nothing else, just being able to see what an end system does while it's gone is a huge benefit to the CISO. So I invite you guys to get involved in this kind of project. We're doing this through the open source effort, and we're and through some partners. And I hope that if you do find this interesting at all, that you can either contact me or get involved in the openargus.org effort and help to bring this to life. So I hope that was enjoyable, and I hope you have some questions.
Thanks, Carter. Right now, I do not have any questions in the queue. So if you do have questions, please submit your questions to the Q&A function on your screen. And we have about 15 minutes left in our time, so we have time for questions. So please go ahead and submit some questions.
Yeah, I hope we get some. So, I mean, this is hopefully this is the kind of thing that can stimulate your interest. And don't worry, you can ask me any kind of question you'd like.
Carter, I do have one question that just came in. It says, what kind of overhead do you see in traffic?
So what do you mean by that? What kind of overhead do we see in the traffic? That can be several...
perhaps generated from the end system.
Load? Yeah, what kind of traffic do end systems usually work with? So in terms of flow data, they don't generate a lot of flow data, maybe 10 to 20 megabytes a day max. And with a lot of minimization, reduction, compression, you can get that down to a megabyte a day. Mm-hmm. In terms of the total data that you might collect from an end system. Now, that, of course, kind of begs the question, well, what are you really collecting? So Argus data looks like traditional flow data, but it has 200 plus attributes, and it has content. So an Argus record can be kind of big. It can be 200 to 1,000 bytes, and you can collect as much payload as you like. You could put 1K of payload in each flow record if you like. So they can get pretty big. So with the right kind of processing, you end up with as much as 20 megabytes of flow data a day for an endpoint. Now, we've got the Argus sensor down to like on a Windows machine and a Mac machine to where it doesn't really go over 0.8% CPU. It sits on the average of like 0.01% CPU, and it's really, really lightweight. It's the same sensor we use for the 100 gig sensors, so we've got it about as optimum, I think, as we can get. And so I think the cycles are really low. Disk, pretty simple. Memory's really small too, because end systems don't have that many simultaneous flows that have to go through, so you don't need a lot of memory. So in terms of transmitting that flow data back up to, say, a centralized collector, it looks like 64 kilobits a second for the most part. It looks like a voice call if you're doing it continuously. And if you're doing it, if you're going to blow 20 meg once a day, and you got a good pipe, it's not a whole lot of traffic to send the flow record back to the centralized collector.
Okay, here's another question, Carter. My research is very close to this presentation. I want to know if there are specific links where I can read more about the contents of this presentation.
Links. No, this is the first time we're actually presenting this work publicly, but we had a lot of presentations that we used for some of the government project people who were interested, and I can share that stuff with you. If you just send me some email, I can send you the slide decks, if you'd like.
Yeah, and just for everybody, we will be posting this presentation on our website. And so, Carter, if you do have a short list of links that are useful, we can post those alongside it on our website, so people can go about it. And I've also captured the email of the questioner, so I'll send that to you, Carter, as well.
Cool. So there are many, many aspects to this project, and it wasn't a simple one because, okay, let's generate some data on an end system and see what we can get. Ended up being a whole cascade of requirements. So just the sensor modifications to go as fast as we're doing was a lot of work. So and the analytics to set up for the predictive analytics framework was an awful lot of work, and a lot of that stuff is supported by our partnerships. I was going to show you guys on the open. Do I have the screen? Can I grab the screen back again?
You have it now.
Great. I'll just show you guys on our website, which is openargus.org. The first page, there's an Argus plus machine learning section. So if I go to the read more by clicking on that, down here towards the end, there's specific projects that we work on through the open source stuff. Counterflow AI, Oak Ridge, and Stratosphere IPS. Stratosphere, I think, is in Czechoslovakia, Eastern Europe. Counterflow is Virginia, Oak Ridge is down in Tennessee. So I would love to add more projects to this list. And so if anybody's interested in that kind of support, we'd love to get involved with that as well. Okay.
Carter, I did see one question come in through the chat. What is the lag between intrusion detection and possible intrusion?
Oh, you mean from in terms of analyzing in a system like this, do you think?
Yeah, I'm not sure. That's
yeah. So let's assume. Yeah. So one of the reasons that this is a successful strategy for this independent SOC at DHS is that their turnaround time is not in the minutes; it's in the days. And so for data collection, processing, the alarms and alerts and reports to be generated overnight, and for a CISO to take a look at them in the morning is a common and average time cycle. If you wanted, so this kind of technology is really oriented, like I said, around the NSA IACD strategy, which is really a near real-time SOAR-coupled infrastructure so that they can do this wire line speed sort of response to on-the-wire behavior. And in that case, the Argus components can be tuned and such that they generate data within a second of stuff on the wire. And if your analytics are really fast, you can mitigate, possibly theoretically in under 2 seconds. So from something being on the wire and you in recognizing that it is an attack and then being able to respond. A lot of the universities use this kind of strategy now to do their own sort of homegrown, show me all the IP addresses, and I'm going to manage my IP filters and my routers and switches based on the data that comes out of this kind of an architecture. And they're in the sub 60-second range for mitigation, if you want to formally call it network mitigation. And so it depends on the threat model, depends on your interest, it depends on your ability to respond. But I like the notion that this is somewhat time independent in the sense that I may be looking at data from 2 months ago, and I realize that this guy got broken into then. What am I supposed to do now? Well, there's still responses that you need to do. And so I would like to think that a lot of the response time is can be considered to be time insensitive, which is completely different than what, say, the DoD or some of the traditional network cybersecurity people want to hear. They want you to be able to do something right now. But I think that there's always room for the protracted detection and response model, which allows you to do an awful lot of interesting things and a lot of very sophisticated things to minimize false positives and to get to the real problem. I hope that was helpful.
I think so. Mike, do you have anything else you see in chat? I think that's all the questions that I see on the Q&A.
Well, I think that my approach, which is to say, oh, you want to do machine learning, you want to do predictive analytics, okay. The hard part is the data generation, creating good data that has the right features in it that you need and want. Collecting that data and managing that data, that's really the hardest part in predictive analytics today. There's so many machine learning strategies that are available. They're doing a really good job. There's a lot of cycles, and GPU-enabled analytics are helping to make this approach a useful approach. But whatever model you create, whatever algorithm you decide you want to use, you have to put that back into a data stream. You have to use it to analyze data. And so it all comes back to the data and the data architecture. So I wanted to focus this talk on let's get sensing to the endpoint, let's collect that data in intelligent ways into a framework, and then let's enable predictive analytics for the enterprise. And the specific analytic is not nearly as important as enabling a system that allows you to run many analytics. And so I hope that I didn't kind of fake people out by saying that I was going to do predictive cyber analytics and not talk about specific algorithms. But I think the hardest part is the data and the feature set. And if you look at the literature on using flow features, network flow features for intrusion detection or for anomaly detection, having really good features that generate reproducible results for either deep neural networks or vector type systems, K-clustering, all of that stuff really requires solid, well-engineered data. And so I hope that in this talk, I kind of got the point across is data, data, data. Be sure and generate it intelligently, collect it and manage it, and then hang a lot of analytics on top of it in order to improve the cybersecurity postures for enterprises. I guess that's the best way I can kind of summarize it all. If you want to use this system that we developed at DHS, it only costs $1 billion. And so, come on, let's go. But if you want to try it out, send me some email, and especially if you're an organization that would seriously like to play with this technology, definitely would like to talk to you about how we might be able to make that available to you. And if you're a government research center and have some funding dollars, that'd be great. We really like that kind of stuff.
That'd be great. Mike Ficosi, can you turn on Michael Hines' microphone? He has his hand raised. We'll see if he has any questions. Michael, I think your mic is open now.
I had a question. A lot of the data, of course, now is flowing through the HTTP ATP security. So are you actually doing content analysis of that traffic?
Absolutely. Yep. So the Argus data, you can read about this. So it has lots and lots of features, well-structured data elements, but it does have content. So you control how much content you capture on a per protocol basis, even on a per port basis. And if you configure it right, you can get 100% of certain protocols like DNS, DHCP, ARP. For protocols that are totally unknown, you might get a fixed snippet of data. We normally use content to verify protocols or verify encryption or to verify services that are supposed to be on particular ports and particular flows. But the idea is that if you tune it right, you hopefully can capture the data needed to do just about anything you need to do. The Argus project was designed to audit network traffic in a way that allowed you to do network forensics much later on. And the idea was that if it's the only thing that you're going to store on disk, you ought to pack it with as much data as you possibly can. So that's where the content came from, and that's why content's so important that we have.
Thank you.
But it's kind of, but I think the best way to think about it is that a shallow packet inspection instead of deep packet inspection, because we may only get the first 128 bytes, and then you're doing the content analysis later, right? So so it might be, think of it as shallow packet inspection, but for the most part, I think you get just about everything that you need.
All right, thanks.
Yeah, absolutely.
Cool. Well, very good. I do not see anything else in the queue, so I do want to thank Carter for taking time to chat with us today. It's been an outstanding talk. I think we've had a good mix of talks during the course of this seminar series, so I was delighted we were able to get Carter on board. I do want to remind everybody that this session will be put up on our website, and we'll try to get some links perhaps to this research that we can put alongside of it. So if you have some deeper questions, you can get into it there. A reminder that next week on August 5th, there is no seminar. So we're not going to hold this seminar next Wednesday. So everybody gets a week off, and we'll start again on August 12th, and we'll do our last two leading up to the start of school on the 12th and the 19th. So I just wanted to tell everyone thanks for joining today. We appreciate your time and attention, and we'll look forward to seeing everybody on August 12th. Thanks.
Thank you.